My name is Hamad Jamshedfar. Today I'm going to continue my previous video working on beams and finding the graphs of bending moment, shear force on the different type of beams. And if you remember from the previous video, in the previous video we were interested to find the reaction or internal forces and moment in a specific point like B. For example, if I cut this point and I put the reactions which are applied by the other section of that to this piece, we had three static equilibrium equations, and by solving those three equations we could find these three unknowns. The meaning is that we can find whatever is applied at point B. That was the thing that we discussed in the previous section. For example, we solved an example like this. We were interested to find the reaction forces and moment at B. The first thing that we did was just replacing the forces, the distributed forces with single forces, and then we found the reactions which were applied at B to keep this structure, the cut of this structure in the static equilibrium condition. That's a point. Right now in this lecture, I'm trying to show you what is happening if you have a beam like this. For example, you may have a distributed load here, you have a single force over here, and you're interested to see what is the value of shear force all over this beam, and what is the value of the moment all over this beam. The idea here is that instead of doing cuts, many cuts for different points, we can have plots, meaning that a plot which is presenting the shear force and a plot which is presenting the bending moment. What is the point of having these plots? We are interested to see what is the maximum thing when you are designing. For example, this could be a bridge. You have, for example, a distributed load, a single force, and you are interested to see what is the weakest point, or where we have the maximum bending moment. And we design for this, we make it a structure with the same cross section all over the bridge. But the point that is important for us is the point that we have the maximum things. For example, here I have the maximum shear. I can consider that if we are interested to design based on the shear, and here we can consider the bending moment. Usually it is bending moment which is causing this whole system to fail, and that's why we are very interested to go from V to M and find the maximum moment which is applied on the system. Then the idea here is that how we can find the plots which is showing me that how much is the shear force in different part of the beam, and also how we can find the moment, bending moment in different points. And using these plots we can go ahead and find the maximum one and have a good understanding of where the maximum is and how much is the maximum moment applied on the beam. This is the idea behind that. I have actually two approaches for finding these things. The first approach is using the formulas. We have two formulas and we can use them to find these plots. But I'm not so interested to use the plots, use the formulas. I like to show you how to do that by just finding the areas, and but I start with the formula and show you how to understand what's happening and then go ahead with the areas and show you what is happening. Before doing that, I just need to find the reaction forces, meaning that I need to know what is happening here and what is happening here. This is the first step for any question of this type. Then the step number 1 would be finding the reactions. Okay, let's find this together. For example, you have a force here which is applied at point x2, actually point with B. You have a distribution of load which is, for example, W, and the length is here A, and what I have is for the reactions I have a pin over here, name it A, the other one B, this is a Y, this is a pin, we have 2 forces for that, the other one B is a roller, I have BY only. You know, this is 3 unknowns and we have 3 equations to find the values. For finding that, we can write down the equations. I know AX, sigma of x is equal to 0, we have only AX equal to 0, this is done. For y, I have BY plus AY equal to P plus omega times A. What is omega? It is a distributed force or distributed load. And the unit of omega is, for example, Newton per meter. You need to multiply that to a length to get a force. And that force is, I'm just using another color, is exactly in the middle because this is a rectangle. You put W times A instead of this guy to find the reaction forces. Then instead of this distributed load in this stage only, you just put the result of that, which is W times A. Right now I have 2 unknowns. I need another equation which is sigma m. I do sigma m around point A equal to 0 and consider the counterclockwise as the positive direction of the moment, and then start to take the moment around point A. What I would have is this. WA is a force and it has an arm. The arm is the middle of this because we put this as the result of the distributed load in the middle of that. Then this is WA times A over 2. P is applied. This is negative actually. The other one is negative as well because they are making clockwise and we consider counterclockwise as the positive. P times B, and what else I have making moment is BY, which is positive. BY times L equal to 0. If you solve this problem, you can find BY, meaning that BY would be WA squared over 2 plus B times P over B, actually over L. This is BY, and right now you know the summation of BY and AY is P plus W times A, and if you replace this BY over there, you can find AY. And this is a parametric problem. We can solve that by some numerical values for these guys, but let's go with this. And this is what we get for AY, which is omega times A squared over 2 plus P times B over L. Okay, let's assume we have some values for these guys. The second step after doing that is doing the plot again with exactly the distributed loads and the reaction forces. Right now I know my AX is 0, I don't put it there, but I know I have a value for AY and I have a value for BY. And let's see what is happening. I just do some dashed lines. Where I do that is where I have some changes in the distribution of the loads, meaning that I'm doing these dashed lines and bring it down to make sure that I have the changes on the other plot. Okay, let's go ahead here to see what is happening. As you can see, we have a jump for the shear force, meaning that I start from here. The goal here is to do this plot. I have a jump, I have a reduction because of this, I have a constant value, nothing here. I'm going down because of P, and nothing here. I stays there and jump up because of BY. This is what is happening here. For doing these things, we have formula and we have an approach. We are interested to see what is this much, what is this, why this guy is line. This is constant, this is line. This is 0, this is constant. This is 0, I mean the distribution of load is 0 here, the distribution of load here is 0. The distribution of the load here is constant. When it's constant, we have a line with a slope. When it's 0, it's constant. When it's 0, it's constant. We want to see what is that. Okay, let's assume we have found these guys numerically, and I know how much is this, how much is this, and how much are these things. I want to show you what is happening for the plots. I erase this part and try to use the formulas and then try to use the other approach, which is much easier. Okay, let's start with the formulas. The formula is saying this: V, which is the shear force, is integral of W dx plus V0. This is the first formula that I have. Second one, M, is integral of V dx plus M0. These are the two. What this one is saying is this: for finding V, we have a V0 always. For example, here, for finding this V, we have a V0, which is this guy, the beginning of that. And we need to find the integral of W dx, meaning that this is W and we consider a negative value for that because it's downward. For example, -2. And then take this integral and add it to V0. What is happening here is like this. I'm taking this integral for different value of x, starting from here. The more I go, the less this value would be. For example, if I have this guy, V, at point, for example, 1. Let's assume 1 is smaller than x1. And I'm taking -2 dx plus V0. That would be something like this: -2x from 0 to 1 plus V0. As you can see, that would be -2 times 1 plus V0. And the more you increase the value of x, the less value you will have for V. Okay, let's keep it simple. This is the integral. What is integral? The area under the surface. This is the surface. I have this surface. I'm taking the area of that. The more I go, the more reduction I have for V. Integral of constant is a line. It's negative and the slope is negative. Then what I get at the end of the day is a reduced value with respect to V. What is happening here for V? Again, I need to write it down, but this time I have no integral, meaning that this is V0 at the beginning. I find another point. This point is found. How? We have V0 minus omega times L. This would be V at this point. Name it V of x1. We know Vx1 is V0 minus omega L. Omega L, what is omega L? It's this integral. What is that? This is the area under this. What is the area? It's a rectangle. Easy. This would be omega times x1. Actually, it's x1, not a. Yeah, x1. Actually, a. Yes, a is correct. x1 is something in the middle. Yeah, this is that value. We need to do the integral again, meaning that I have another v, which is again the same formula, but this time I'm going from x1 to x2. Then I put Vx1 as my brand new v0. Here I don't have any value for omega, meaning that omega is 0. The integral of 0 is 0, but we have Vx1, meaning that that's why this value stays constant. You are reaching a point like this. This P is like an impulse. Bring this plot downward to another point. And you don't have any value for omega. This is just a point. You see that shifting down the plot. You don't have any omega. This is 0. You stay there. And at the end of the beam, you have Py, jump up. This is what is happening for V. Okay, let's do a review. I have jump up because of this guy. I have a distributed load which is constant, getting down. I have nothing. It stays there as a constant. I have an impulse like this, getting down. I have nothing. It stays whatever it is. I have By and it gets back. Okay, this is what is happening for V based on the formula. I want to show what is happening for M. M is doing exactly the same thing, but this time with V, meaning that it starts with a 0 value, M0, which can be a value or 0 for different problems, taking the integral of Vx. Actually the function of V, which is a function of x. Right now, we start from this point. This point is a hinge. Hinge is not providing any moment, we know that. This should be 0. And it should get back to 0 because we have a roller over here. Okay, then I know my M0 is 0. What is this? This is the integral of V, which is a line. The integral of a line is a parabola. This is x. This is x squared. A function which has x in it. This one is a function which has x squared in it. I reach a point. This would be my brand new M0. This is a constant. What is the integral of a constant? It's a line. You reach a point. This is another constant. What is the integral of that constant? Is another line. This is positive. The slope of this guy is positive. This is negative. The slope of this guy is negative. Meaning this. I'm starting from 0. I'm going to reach a point. What point is that guy? Is the summation of this area. The area here is add up to the value of M0, bring you up. The area here start to increase because this is positive, it's still positive, bring you up to this point. From this point, you have a negative value, which is added to M and bring you back to 0. This is what is happening. Okay, that's the way that we are using these two formulas, but we are not so interested to use the integrals, and we are good with using only the plots. I would say you have omega and you are looking for V and m. And let's see what is happening. Omega could be a rectangle, or it could be nothing, or it could be, for example, a ramp. Let's see what is happening for these guys. I just consider two plots and show you what is happening there. If it is 0, like this one or this one, you usually have a constant value for V, and you have a ramp for M. Look at here. Here I have 0, I have a constant value for V, and I have a ramp for this guy. This ramp could be upward when this is positive, or downward where this guy is negative. If you have a constant value for omega downward, it's in 95% of the problem is downward and its value is negative. What you would have for V is a line, because its integral of constant is a line. And what you have for M is a parabola, something like this. Meaning that I'm taking the integral of a constant, that would be a line, and it's negative, it's downward. And I'm taking the integral of a line, and the area under that would be positive, going upward. And this is x to the power of 0, this is x to the power of 1, this is x to the power of 2. But if I have a distributed force like this one, what is happening for V, what is happening for M? For V, what I have is a parabola. That means something like this, you would have its x squared function of that, and you're taking the integral of V for finding M. What you would have is a cubic, x to the power of 3. You can make it general, meaning that if I have a function to the power of n, for example, whatever, x to the n for omega as a distributed load, what I would have for V is x to the n plus 1. What you would have for M is x to the power of n plus 2, meaning that you would have some curves for these guys, and you are increasing the power by 1. Here I have x to the power of 0. Actually I have 0. Then I have x to the power of 0. Then I have x to the power of 1. Here I have x, I have actually a constant. I have a constant, meaning that x to the power of 0. Here I have x to the power of 1. Here I have x to the power of 2. And here I have x to the power of 2, x to the power of 3. If you have x to the power of n, x to the power of n plus 1, x to the power of n plus 2. Right now, having these things, you can solve whatever question is given to you. You just need to consider the initial value, meaning that here I know I have an initial value because of this jump up. This is a distributed load and it's negative. What it has on the effect of this on the V is going downward with a line reaching here. How to find this? See how much is the area here, reduce that and subtract that, get to this point, stay there, because this is 0, you stay there. And here I have a jump shifting down, here nothing, stay there, go up. Okay, from here to here I have 0 because this is a hinge. I'm just going up because this is a positive, I'm taking the integral of that, reaching a point. Where is that point? The area here. This is a trapezoid and you can find this value. Going up because this is a constant with a line, this is parabola, this is line. Going down because of the negative value and you should get back to this, to 0. This is a checkpoint. This is the idea how we can use these plots, and in the next video I will show you how to use these concepts to solve different examples. Thank you so much.